I don't just want to speed up my Python code. I want to speed up how quickly I can write my Python code. Welcome everybody, I'm James Powell, and today we're going to be talking about tightening your iteration loop. We're going to talk about how to improve the process by which you deliver code, whether that code happens to be very fast, very high performance code, or just code that solves a simple problem for yourself. I want to answer for you a couple of questions, but I want to give you some principles, overlapping principles, that I use to decide whether my iteration loop is as tight as it can be and whether I can improve it. Before I get into those principles, I want to talk to you broadly about some motivation for this. But note, I am as guilty as anybody of giving advice that I might not take myself. And so there is room for improvement in all of our processes. I know, even putting together these notes, that there's things which I've slipped a little bit on doing that I need to do a little bit more of in my work. Well, let's take a look. When we talk about the iteration loop, we can analogize this to another loop you may have heard of, the OODA loop introduced by John Boyd in the 1970s. This is the observe, orient, decide, and act loop that was used by fighter pilots in order to improve their operational efficiency when dogfighting. And the general idea here is that the tighter their OODA loop, the more effective they can be in these very fast-moving situations. Specifically, that the idea of higher agility can overcome raw power. You may have even seen this in some cases where we have done sessions on topics that we are not experts at. For example, I'm okay at JavaScript. I am not a JavaScript expert, but I can churn through JavaScript code very quickly because I have a fast iteration loop. And so when I don't quite know what I'm doing, I can try a bunch of different things and then quickly orientate myself around, okay, I think this is what's going to happen. Here's my hypothesis. I can act and then tighten that loop and see did that work or not. When we talk about our iteration loop, we're typically talking about something that can be measured by the time that it takes between making a change and seeing the effect of that change. And one of the dominating principles, I think, of tightening that iteration loop is making sure that you can make a single line change to your code and immediately see the result. Many of the principles that we see will overlap with this idea or further empower this idea. But the general idea is something like this. And you've all seen me do examples like this before. I have a pandas series. I say, oh, I need to do some operation on this pandas series. And in order for that operation to work, I need the index levels to be swapped. Is it a swap levels? Nope, it's not a swap levels. Is it a index.swap levels? No, it's not an index.swap levels. Is it an index.swap underscore level? Nope, it's an index swap level. Okay, there we go. And I guess maybe I don't need to perform this on the index. I can perform it like that with then a reset index or a sort index afterwards. Ooh, let's close some of these. And what you can see here is the idea of the iteration loop. I don't know off the top of my head what the names of all the different methods in pandas are, but I know that if I can quickly make a change and see the result of that change and immediately see the result of that change, the tighter I can make that, the faster I can go. I can actually trade off meticulous memorization of the details of these with just moving very, very, very quickly. There are some general guidances that I have for my own iteration loop in order for it to be effective. One, I generally want that iteration loop to be under about a second. This is something that's a little bit controversial because when we talk about things like unit tests, there's a lot of guidance here that your unit test suite should either be runnable very, very quickly, or it should be hierarchically structured so that the most obvious tests run very quickly, and then the more sophisticated or the more nitty-gritty tests run, at the end of that. But a unit test suite running in under 1 second, or a continuous integration pass going in under 1 second, that's quite aggressive. It's my view that it's not necessarily 1 second that we want this to be less than, but we want this to be less than the speed of our actions. That is to say, I want to be able to see the result of an action I do faster than it takes for me to perform that action. So even though I might fumble a little bit when I'm typing, I might make a bunch of typos, it's generally the case that I can see the result of this more or less as quickly as I can type these results. In fact, if I had set this file to auto-saving, I might even see those results stream on me as I go. And as a consequence, I'm not waiting, or I'm not trying to batch up my actions, or I'm not seeing some poor synchronization between my actions and the results as a consequence of the iteration loop being too broad. You've all experienced this. In cases where that iteration loop might be 3 or 4 minutes, you have to kick off a process that runs something else. You'll kick off the process, a compilation, a unit test suite, whatever the case may be, and 3 minutes into running it, you'll say, oh, I just spotted there's a typo there. And you'll kill the process, and you'll start over with the typo fixed. And then 2 minutes into the next run, you'll say, oh, actually, I forgot to unpack this structure. Another trivial error will hit you. And it's generally the case that unless you take a deep breath and you plan out each of those steps and you batch those up, well, it's the case that you're going to see this just dragging on and on and on. I know you've all seen this happen in your work where there was some script and there was some error in that script and you fiddled with it, but nothing seemed to work and you were just wasting your time. And the longer it takes for you to see that that didn't work, the longer this stretches on. Generally, what I see is that the speed of your overall operation grows non-linearly with the tightness of the iteration loop, which is to say that basically if it's under the speed of your action or near the speed of your action, that's one regime. Between maybe 1 second and say 10 seconds, maybe the speed of your attention span, that's another regime. So I don't think a 2-second iteration loop is actually twice as efficient as a 4-second iteration loop. I don't think that's really the case. But I think that within some regime tied to the amount of attention span you have or the amount of time you have before you start wandering or you start thinking about something else or you start evaluating something that you pre-assess something else, that's another regime. And the other regime is anything longer than that. I think past a certain point, it is the case that a 2-minute iteration loop may genuinely be more than 2 times slower than a 1-minute iteration loop. I've experienced this myself in cases where a altogether not particularly loose iteration loop, maybe 3 minutes, ended up with me working until 10 or 11 p.m. at night to solve a problem, even though the total number of passes that I had were very few because there are all these nitty-gritty details. When you think about it, when the iteration loop is larger than the speed of your smallest incremental action, then necessarily you're going to have to batch up those actions. But what that also then means is every change that you see is subject to multiple, or every result you see is subject to multiple changes. So if you did 5 different things, you changed 5 lines of code, then you kicked off your 1-minute unit test, and there's a failure, how do you know that it's not somewhere in the power set of all 5 changes? When you tighten that iteration loop down to the speed of one individual action, then you're guaranteed that the mistake that you made is a consequence of the exact action that you performed. And you can see how if you have something akin to an OODA loop, you're actually tightening that decision action portion, the setting of a hypothesis, and then the testing of that hypothesis, the acting on that hypothesis, and then reorientating yourself. Now, there are certain principles that I apply when I set up my iteration loops in order to be as tight as possible. And one important principle is the principle of isolation. Whenever I'm setting up my iteration loop, I aggressively isolate. And this means many different things in many different areas of the work that I do. For example, if I'm working on some data problem, and in that data problem, I have a very large set of data, I do not run my analyses on the entirety of the set of the data because honestly, most of the time in the initial steps, the mistakes I'm going to make are trivial or superficial or obvious when performed on just one data element. So you'll see whenever I'm mapping something out, you'll see breaks or you'll see islices. I'll operate on the smallest possible representative data set in order to see, did I do something just completely pointless? Did I misspell eig? Is it eigen instead of eig for computing the eigenvalues? And once I'm satisfied with what I have, then I remove those breaks and then I say, okay, now it seems to work. Oh, it doesn't seem to work on this particular data item. I narrow myself down to that item and then go on. It is very, very tempting to try to run all of your code on the entire data set that you'll actually operate on. I know I have wasted so much of my life doing that, but whenever I remind myself, no, I want to move quickly, I always think about how do I reduce the data set that I'm operating on as aggressively as possible. So for example, if there was an error later on here, for example, I've got 3 of these, maybe if I had 30 of these, in the 29th of these, it might be very tempting for me to say, oh, that's just a tiny error. Let me just keep running this main loop. And then it'll pop up on the 29th issue. Maybe I got something wrong mathematically, but that is not the right idea. What I really should do is I should subset this down to the erroneous element and then get it working on the erroneous element, and only then do I lift that back up to all of the elements. Otherwise, I'm just going to be wasting my time and I'm going to be loosening that iteration loop to my own detriment. When we talked about things like web scraping, you would have seen some other tricks that we have used. For example, I recently did a presentation that made use of this third-party library, yFinance, that allows you to pull data from Yahoo Finance. And as part of that presentation, I pulled some option data. Now, you can think that I'm already doing a pretty bad job of my iteration loop if I do anything moderately complex, because making those HTTP requests to Yahoo Finance are going to take time. And it's very likely that if I do this across many tickers, it's going to take quite a bit of time before I can even try to do the analysis I want to do. And so, obviously, I'm going to narrow myself down to maybe looking at one ticker initially, and then only once I'm satisfied, look at maybe another ticker, see if there's any errors, and very carefully and judiciously move to looking at the full data set. But even when I'm looking at just one ticker at a time, these two calls are actually still fairly slow. They're not incredibly slow, but you can see that there's still maybe a half a second there. And so any additional analysis I do on top of this is already pushing me into the territory outside of slower than the speed of my action. How do I solve this? Well, while I'm solving this, one other thing I can consider is, what is the downside to discovering that I've gotten rate limited by the API? In fact, isolation is not just about isolating the dataset, it's about isolating you from the rest of the world. Do I really need to be running the live query every time I run this iteration loop, every time I test something? Absolutely not. Because I could get rate limited. I could discover that maybe the API has changed. I'm just over a release of that API, and maybe the API change is very subtle. Maybe it's not that important. Maybe they renamed a column of the pandas data frame that they return. Whatever the case may be, is that something that I want to have to worry about? Notice that that confounds my analysis. I've set up a hypothesis. This is the way to perform the analysis. I test that. I quickly come back to my starting point, but I discover something went wrong. Is that the thing I just tested or some outside factor? And so I not only want to isolate myself down to one data element, but I want to isolate as many factors of the outside world. When we did web scraping, one of the things that we suggested you might do in order to prevent yourself from being rate limited by the web scraping or prevent yourself from running into other problems is to use some conceit like this pickle cache, where this pickle cache gives you the ability to decorate a function and to transparently pickle that function such that subsequent calls to that function read from the cache as opposed to read from the live API. It turns out that this actually works fairly well. If I were to create a new cache here, you can see the very first call is slow, but the subsequent calls are fast. Actually, to make this a fair comparison, I really should print these out individually because the print will block. So here we go. So let's give this a new cache name. And we'll see the first call will be slow and the remaining calls will be fast. And then every subsequent call after that is now reading from that cache. When working with this yFinance API, I might try something like that, but I'm going to run into trouble. Here, if I try that by, for example, subclassing their yFinance ticker object and putting that pickle cache on this method that I anticipate to be the slowest one, I'm in trouble. My motivation here is a good one. Generally, whenever I'm trying to isolate, I want that isolation to be something that I can drop in and out of. Something like a break that I can comment out and then recomment. This is why I maybe more commonly might use a break as opposed to something like an islice. Imagine the difficulty of turning an islice on or off is actually quite hard because I have to either change this line here or remove it. I might even, if I'm doing like an islice, rewrite the header so that the way to turn this on and off is like that, or pull that onto a separate variable. But the reason I wouldn't pull this out to a separate variable is I actually want the isolation to be something that's transparent to my code. I don't want to pull it out to something and then end up with code that I wouldn't otherwise have written. So the intuition here is actually a pretty good one because the code is exactly the way I would have otherwise written it. It's just the case that I'll comment this out when I'm ready to look at the real result, but unfortunately it just doesn't work. And it's not going to be that uncommon for me to discover that some libraries just won't work with these typical conceits. What I'll need to find is an alternative conceit that preserves all of these principles. A core message here is the following. the actual tools matter much less than your use of these tools and your consistent use of these tools. If you see some of these tips and tricks and tools that we share with you in this session and you immediately rush off and integrate all of them into your work, it is very likely to be the case that you will not truly integrate them into your work, but instead very superficially use them and then discover that it's more painful than the approach that you had and in the end not really improve your process. In general, I shouldn't overly fixate on tools like this pickle cache. Instead, I should fixate on what is it gaining me. It's gaining me the ability to transparently turn some code that is blocking my iteration loop by doing too much work into some code that speeds up that iteration loop by removing that extra work and removing that extra dependency on something that's happening in the outside world. Now, I can dig around with this here, and I could try and rewrite this as like an option chain function, but this is not how I would write this code in the end. I wouldn't write a Python function called option chain just so that I could put a decorator on it, and in the end, it doesn't even work. And so I really don't want to change the way in which the code works. I want this to be transparent. And so what I might end up doing is I might end up doing something like writing another context manager, something very simple here that gives me the ability to take the original code the way I would actually write it. This is how I would actually write this code. And to transparently add just a little bit of detail to it, this context manager here that was written just for the purposes of this example, that gives me the ability to skip if it's already cached or to save this thing. This is a little bit clumsier than my original pickle cache. And it's definitely the case that I could improve it, but what's important here is that the tool itself is not what I'm focusing on, it's what it gains me. It gains me the ability to write the code the way I otherwise would, but then to isolate the portions of the code that I'm paying attention to as I iterate on, for example, the inner portion of this comprehension syntax in order to access the different option chains for every maturity for this particular option from this Y finance library.